First off, just some reminders. I know you have those books that the prior instructor, Professor Squires, I believe, had put together for you. No, who was it? I'm sorry.
Somebody from Eaton Canyon.
Oh, someone from Eaton Canyon. I'm sorry, you did tell me that. I apologize. So there's good information in there, but it's also focused a lot on Eaton Canyon, which I knew when I read it. So just some basic reminders as we get started, the differences between minerals and rocks. So minerals, and the basic words we always say are naturally occurring, inorganic. Those are the two keys, but this is all from the U.S. Geological Survey. The orderly internal structure has to do with their crystal shape, so the chemical composition, etc. So when we have a mineral, it's going to be the pure mineral. And the examples of the most common ones we have certainly here in California are these quartz. It's funny, feldspar is actually there's more feldspar than anything else on Earth. But a lot of it is underground and we don't see it. So quartz, of course, makes an appearance. It's bright, it's white, we see it, and we're aware of it. So there's a lot of thought that that's the most prevalent mineral. It is actually not. Feldspars are. Micas, those are those real flat ones. They're two-dimensional. Well, they're really three-dimensional, but we perceive them as two-dimensional because they're platy. Amphiboles is a large category of very hard minerals. Olivine is the green rock that comes from volcanoes. Now, if it's deep in the earth, we call it peridot. But once it's come out of a volcano, we call it olivine. Anybody ever get an olivine ring in Hawaii? You guys are probably all too young. I have olivine rings that my mother and I got 60 years ago in Hawaii. So, and calcite, which is just calcium carbonate, which is omnipresent. So those are minerals. A rock is an aggregate of one or more minerals. And that sounds weird because you're telling me that a mineral can be a rock. Yes, it depends on the shape, the form, and often it will be primarily one mineral, but it has other contaminants or other ingredients like iron. Iron is a very, very common mineral element in our environment, and so things become colored. Red, in some places green. So the rock may really be, we think of it as just that one mineral, but it's colored by impurities. A body of undifferentiated mineral matter, so that's what I was referring to there, but it's usually combinations. And of course, granite is again omnipresent. Now, a little later, if it's not pouring rain, we'll go outside and look at the different rocks outside, because granite is this weird term. Granite with a small g pretty much indicates anything that will get to an intrusive igneous rock. In other words, magma under the surface that rises towards the surface and doesn't break through for whatever reason. Does the pilot light go out and it can't make it out? Or does it? By the way, you can all be able to get copies of this, so just, you don't have to write down everything if you don't want to. Anyway, so the magma rises and it cools in place. It doesn't burst out. And so that's called an igneous intrusive rock, and granite pretty much covers 90% of those rocks. Some of them are very pale in color. Some are very dark. Some look like salt and pepper. Some look like black rock with a few gray hair strands in it. There's a wide array. So granite with a capital G would be one of those specific forms. But when I say granite with a small g, it's a wider variety. And then basalt. Basalt is the rock that comes from lava. Well, lava is magma that reaches the surface. I don't make up the rules. I don't know why they have different names, but it's magma beneath the surface. It's lava once it hits the surface. And when it cools, it forms basalt. Now that includes basalt at the seafloor, the bottom of the seafloor, where we have our spreading centers, right? Remember the plate tectonics thing, where the new material comes up through these big ridges in the ocean. That's basalt. Now we look at pictures of the ocean floor and we're like, that's not black. What are you talking about? Well, that's because there have been thousands or millions of years worth of sediment from the shore, as well as dying critters that have settled to the bottom. And so there's a coating of lighter color material. But when those, if they're out far enough in the ocean, it's actually black. Or if they have the equipment to scrape away, you actually see the dark color basalt. And basalt, when I think of basalt, I think about volcanoes, Hawaii, Mount St. Helens, at places like that, where there is the black material. And we won't really talk about volcanics, but there are also lighter colored igneous extrusive rocks, which are these, but we think of basalt. Limestone forms in relatively shallow seas. And when I say relatively shallow, 200 feet range. And what it is, it's composed of the calcium carbonate that is both coming into the water from the shore, washing in, and dead critters. And those dead critters are from submicroscopic all the way up to whales. And so, because our bones are made of calcium carbonate. So anything that dies over time is going to degrade to that. So limestone is the lithified or rock form. Lithification is the process of something becoming rock. Like a pile of sand eventually becomes sandstone, that's been lithified. So limestone, again, is it's not organic, but it has organic components in it that are no longer organic because they're no longer alive. And I just mentioned sandstone. Sandstone can be formed from beaches, from shallow waters, both fresh and salt water, and sand dunes, of course. So depending, if you've traveled around this country, you've probably been in Arizona and New Mexico and seen both the dunes or the sedimentary structures. Glenda's wearing her Grand Canyon shirt, right? There's layers of sandstone in that. Those were actually dune sands. And so we have a wide variety of ways sandstones can form. But here, we're looking at old ocean material. Again, and I briefly covered this, the basic rock types. Igneous, from fire. Latin, it means fire, when you ignite a fire. Hot molten rock crystallizes and solidifies, is an igneous rock. And then, as I mentioned, intrusive is beneath Earth's surface from magma, whereas extrusive is atop the surface from lava. And when I say atop the surface, remember, I could mean the ocean floor. It's still off the Earth's surface just because it's however many tens of thousands of feet underwater. Sedimentary rocks, which are the most common in our visuals. They're the ones that are often on the surface and the ones we might notice because they have those layers. Sedimentary rock we think of as layers. And there are rules for how sedimentary rocks are formed. I'll get that in a second. They're pre-existing rocks and fossils that have lithified. So they've been broken up into smaller pieces. And those pieces can be infinitesimal little pieces of clay all the way up to boulders. And while I'm throwing this in here, it's a good point to mention it. When we talk about rock size, there's something called the Wentworth scale, and it goes up, and we don't need the details, but clay is the smallest particle, and it's 1/256th of a millimeter, I believe. Little tiny stuff. Now, if you go like this in the dirt and you want to know if it's clay or not, put it on your tongue, and if it's, geologists lick rocks. If it's slimy, it's clay. If it's gritty, it's a very fine sand or a silt. So we've got clay, which is the smallest particle, and often clay particles may also be sort of two-dimensional. Again, everything's three-dimensional, but they're so tiny, you don't see them. Then there's silt, which is very, very fine, but again, on your tongue, it's gritty. Sand, you're probably not going to bother to taste it because you can tell it's a sand. But sands come in everything from very fine sands to coarse sands. Fine sands are the nice powdery white ones. Sometimes they're sands made of decomposed rock. I was just in Trinidad, and the sand is ground up limestone bits. It's shell pieces, very small. So, but it's still a sand. But there's coarse sand, which is just a higher grade. Anybody go to the beach in Ventura? That is coarse sand. The reason it's coarse sand is because that sand has been dredged from offshore where the rivers come in and dump it, and it's a coarser sand, and they've deposited it on the beach. The reasoning isn't really relevant. It's just the idea that when you pick it up, it's really granular. So that's a coarse sand. Now, and let me get up, sorry. Then there's pebbles. Kind of know what pebbles are. They're little rocks. Cobbles. We don't have a lot of cobbles in California. Cobbles, right, you think of Britain and the nice flat stones and skipping stones, but those are the next size. And then we have boulders. Now, this is the frustrating part. A friend and I have discussed coming up with our own boulder scale because those are boulders there under the bobcat over here on this side of the room. But so is any rock bigger than what we'd think is a pebble. Then again, there are boulders the size of this room. And it's really a vague term. Oh, it's a boulder-filled stream. So am I going to be walking on those, or am I going to be having to clamber over these huge structures? The name doesn't tell us. So as I said, Vicki and I are talking about coming up with our own. Anyway, so those are the different sizes. And you wonder, why do we care? Well, think about how water goes through those different things, right? Because it's been raining. What are the hillsides like? Are they muddy? Are they dry? Well, obviously, a lot of times in streams, we have boulders, and when the water is low enough and it's not raining, the boulders are dry. But the smaller the particles, the more they retain the water. You've gone to the beach and dug a hole and there's water down there. Well, some of that is coming in from the ocean, but some of it is from the last high tide that percolated down and has stayed wet because the particles are smaller. There's less pore space, there's less openings. So there's no place for the water to go. Eventually it goes, but we know it goes in right away. You ever pour your leftover beverage in the sand at the beach and it disappears immediately? It goes in, but it's wet down below. So we care about sediment size in terms of how it shapes the mountains, what's going to happen. Water flowing over the rocks, it's going to have to be really strong to move those rocks. Water flowing over sand, it has less resistance. It's smaller. The water doesn't just go through all the openings. So that's why we would care in an environment about sedimentary rocks. And I'll show some pictures later that show about how these distinctive layers can tell us about the environment in which they were formed, even if they're all the same stuff, because there are changes in the environment as they deposit. Not all layers are the same stuff. You might have a lava bed covered with ash, covered with sand from some other environmental process. So sedimentary beds can vary a lot in what you look at. Around here, what we've got primarily are alluvium, which I'll cover a little bit. And it's basically the stuff that's come off the mountains around us and has either come down by gravity or been carried downstream by not only Placerita Creek, but also all the little tributaries that float down the mountain. The last type, metamorphic, metamorphosis is simply change. And this just means that existing rocks have been subjected to intense pressure. So where would there be pressure around here? Oh yeah, the San Gabriel Fault, the Placerita Fault, the White Wolf. We have lots of faults in this valley. Those are the biggies. That's pressure. And when we talk a little bit about faults, we know there's lateral faults that slide, but it's not like it's really all that smooth, right? There's a lot of pressure pushing. And so as they go by, there's pressure. But also, if you take your hand and go like this, isn't it warm in there where you had that pressure? You just hold your hands. Well, there's heat generated by those rocks pushing against each other. And then, so that's the sort of the primary way we think of metamorphosed rocks and how they're metamorphosed for heat and pressure. But mineral-rich fluids, usually quartz or other minerals, will come through, particularly if there is any sort of tectonic activity, any activity that's enough to that pressure and heat to heat up some minerals. Some minerals liquefy, melt at lower pressures, and so now you have this water bearing all these minerals, and they can modify the rock as well, because now you've introduced heat, pressure, and a new mineral. So a metamorphosed rock has been changed. So that's an interesting thing. It's kind of like the SOAR thing, only the same thing, I'm sorry, but definitely changed. So, and I know that was in the book. So one of the things that Sandra asked I mention was geologic age dating. How do we know how old rocks are? So the first way we do age dating, and we do it all the time, sorry, didn't disconnect. The rocks below are older than the ones below generally, but stuff happens. Things fall over, pressures push, and something that was flat is now mounded up and tips over. So there's all sorts of ways that we might end up with something being younger below, but generally relative dating. But relative dating is also the idea that you can look around this room and make some assumptions about who perhaps is the youngest person in the room. But you're just making that relative guess. Maybe they're just really good looking for 84, right? You don't know. So relative dating is fairly uncertain. It's commonly used, and we use relative dating in fossils, right? We find fossils in layers, and we think, oh, there's X fossil right here, so these animals lived however long ago, which means the sediment is that old. Maybe not. Maybe that fossil washed in from up there or over there. We don't necessarily know. It's kind of uncertain. Absolute dating, on the other hand, which is an improving science all the time, uses different analytical processes to evaluate the age. Now, obviously, this was the Grand Canyon to show us the nice horizontal layers where we make assumptions about how old things are. The oldest rocks in the Grand Canyon, the Vishnu schist, are truly ancient. They are what we call Precambrian. Very, 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 very old. So, but we have all these different layers, and it's generally appropriate to think oldest, youngest. But when we're not sure, and we want to know a specific age, we can use, now this is a mass spectrometer, so we can use a mass spectrometer to analyze various situations, and I'm not sure if I did another slide. I did, okay. So we can verify the age of the mineral based on its elemental composition. Now that is used, we do this with radiometric dating, sorry. So it is believed the Earth is 4.5 billion years old. Now, 4.54. There's also some stuff out there that says it might be as old as 6 billion. But 4.5 is the operational number. That's the number we use, 4.5 billion. And how did we determine that? Was using this radiometric dating. And there are a lot of other methodologies, to be fair. There's strontium and all different sorts of chemical analyses that can be done that some work better than other rocks. But sort of the most common one is this uranium-238, which becomes lead-206. Uranium-235 over time becomes lead-207. Now the half-lives, we've got 4.7 billion years for the top one, 710 million years for the latter. And again, what a half-life is, it's the time it takes for one half of the atoms to decay to the other. So it takes 4.7 billion years for one atom of uranium-238 to become lead-206. So that's a long time, right? It doesn't take so it has to be a really old rock for that even to work. But we can try it with some slightly younger rocks with uranium-235 that takes only 710 million years to become lead-207. And this is a little diagram of half-life. So if my rememberer works right, there are 32 uranium atoms in this. And then after X number of years, 4.7 or 710, depending which one we're using, now we have 16 of each. Let another 710 or 4.7 billion years go by, and we have 8. Did I count right? Yeah, we have 8 left of the uranium. Another period of time, and we've got 4. Another period of time, we'll have 2. And at the end of however many millions of years, we will have 1 uranium. And eventually, it too will degrade to lead. So it's a kind of a simple math concept, but it takes very expensive equipment, and I'm sure a heck of a lot of patience. But that is kind of the standard way, is this radiometric dating. Again, there are other elements that are used for this. There are new methodologies that involve looking at minerals and sediments to see when the last time they saw sunlight was. So you can, and this is all done like in one of those old-fashioned camera things. You got the hood over you, and you dig a hole, and you measure what's going on in this hole, assuming that that is more original than what you've dug through. So that's one of and that's not all that new anymore, because that was in grad school a lifetime ago. So anyway, that's how we date minerals. Now we end up with these geologic time scales, and the one on the left is just sort of a clock, right? There's 24 hours on that pretend clock. The light gray on the left is the Archean, which means we're still looking at like the fire and we don't really know what the early Earth looks like. Common perceptions are sort of the whole fire and brimstone volcanoes, but there's also evidence that maybe there was water on Earth. It's a constantly evolving field. But the Archean is sort of prehistory. Then we get to where Tina has to make it big to read it. Oh, pardon me. I'm sorry. We started from midnight to 3. That was Hadean. That's the one I apologize. That's truly fire and brimstone. It's the reference from Hades. So that's the very beginning. Then the Archean is we're sort of getting ourselves together, but the idea that there's water is still uncertain. It's still a very rough surface. It's still, the Earth is not yet fully agglomerated. It's still got a lot of gas. It's still doing other things, right? Because Earth, like all of the other planets, came from this big belt of swirling gas after the Big Bang, and different pieces got together. The Earth is terrestrial, it is solid, but it took a long time to sort of off gas. And so in the Archean, it was still doing that. Then, I'm sorry, the Proterozoic, which is from 10:30 to noon, and then again from noon to little after 9 p.m., Proterozoic. That's really right before life starts. So we don't have life as we know it. I think that's from some movie. On Earth. There are, and again, new evidence indicates that there may have been new microcellular structures that we're just learning about, right? Just as an aside, there was this theory that rocks have live bacteria in them, well, yeah, it's coming out that many rocks do have live elements in them. When I say element, I don't mean mineral element, but bioforms. Anyway, all those little colorful things after that are all of the different eons and eras, and we've got like up there, let me see, can I get to, hello. We've got, starting here with the Precambrian, which is what we'd say before that purple one. It's real old, and then the Cambrian, and you've heard these, Ordovician, Silurian, moved it up a little bit, come back down. Devonian, Carboniferous. We think of Carboniferous as being when things were dying and we had a lot of vegetation that was dying, so that's where oil comes from. The Permian, Triassic, Jurassic. Who was around in the Jurassic? Dinosaurs, right? But even that is a misleading concept. I'm sure you're aware that there were different forms and they weren't all around up till 65 million years ago, but they pretty much all died out when that big old asteroid hit, about 65 million. Cretaceous, Paleogene, and Neogene. So we're in the Neogene, sort of the new part. But this chart on the bottom, of course there will be a test on this. Sorry. This is a very complex, and they come out with a new one every year because someone will find some age of rock in a new place and have to stick it in. But they go down by the age in millions of years. Use this instead. Well, no, do this. The eon, we call the eon like the Proterozoic. Well, so we started here, Archean, Proterozoic, Triassic, Jurassic, Cretaceous, Paleogene, Neogene. Those are eons. Eras are smaller divisions, and the way they're broken up, excuse me, reflect different global climate situations, global landform movement, where they, like, who's connected to who, and what kind of animals, or life forms rather. Period, that's really close. So we've got, there's Ediacarian fauna, which is completely different than whatever that says. Sorry, I'm too close, but such and such else fauna. And then the end of year ages. So anyway, obviously, I'm sure there are people in the world who've memorized this, and I don't know who they are. But that's an idea of how complex Earth's geologic history is based on different places. And there'll be what should I call it? There'll be a period that we find in England and Scotland that we don't find anywhere else on Earth. Or there'll be a period that we found in North and South America that we find nowhere else. And because of different changes on the surface of the planet, again, as the plates moved around and sea levels rose. And I'm sorry, do you have a question?
Yeah, are places on the Earth that have a warmer year-round climate more or less likely to have more areas?
No, because they weren't always warmer. That's the trick. That over the last 4.5 billion years, and we really haven't had continents as we know them except for about the last 3 billion, they keep moving around. We've had supercontinents like Gondwana and Pangaea. And so the continents as we think of them now have come together, split apart, sometimes not like they were when they merged together. New ones spring off. So we might find fossils reflecting a very wet environment in the middle of the Sahara. Because at one point, what we now consider North Central Africa was way down towards the South Pole. So that's part of the problem. And we've also had climate change, global climate changes that are caused by Earth's relationship with the sun and our orbit around it, what the shape of our orbit is. There's all sorts of different Milankovitch cycles, or what they're called. This scientist came up with 4 different cycles that have to do with the wobble of the North Pole, the way that the pole drifts, the fact that our orbit around the sun is not always, it's never a perfect circle around or very rarely around the sun, but it changes over time. And there's also times where my computer's the sun and the orbit now goes like this, way around, and then passes around again. And then other times where it's kind of in the middle, and then another time where the orbit would go way around that way. So temperatures on Earth and climate conditions can change because of what's going on in the above the atmosphere with the sun. So yeah, the fact that it's warm now doesn't mean it was 100,000 years ago. So, sorry, come on. So, the big picture history of this region, sort of like, so what did this whole area look like millions of years ago? And it's kind of funny because the only time I'm from South Bay, Hermosa, Torrance, Long Beach over the years. I'd never, what's Santa Clarita? It's where Magic Mountain is. And then I did a mapping in 1981. I was already graduated, taking classes at community college for fun, and we came out and mapped someplace on Bouquet. And I had no idea where I was until about a year ago when a friend who'd been with me all those years ago, we were driving along, and she looked up Plum Canyon and said, that's where we were mapping. Obviously, there were no homes, there was nothing. But anyway, so I did a paper on what happened out here in the Miocene. So this, I'm like, oh yeah, I remember that. So the Miocene epoch, 23 to 5.3 million years ago. Sea level was fluctuating around the world. It would go up, it would go down, up to hundreds of feet in differences. But at the end of that time, it was generally falling, so globally. But nevertheless, this area throughout southwestern North America remained underwater. We had an inland sea east of California in Arizona, New Mexico, and on up into Utah, even later than that. But we were still underwater. So hence marine deposits, right? Then in the Pliocene, which was 5.3 to 2.6 million years ago, sea level came back up. And that's what gave us our marine formations along the California coast. Anybody familiar with the Palos Verdes Peninsula? There are 13 what we call marine terraces on the Palos Verdes Peninsula. A marine terrace is formed when sea level is at level X and the waves are breaking and it levels off the ground. And then either sea level drops or the hillside rises, which is what happened in Palos Verdes. That happened 13 times. Now, when I was a child 29 years ago, we could look out and see 8 different marine terraces. You could still see them. Today, if you have a vivid imagination, you can see 3 because they've graded them all and there's homes and vegetation. But structurally, there are 13 marine terraces. How about Big Sur and up there along the coast where you're driving on the highway and you get to the part where you're no longer on the edge, but there's all those green fields you're driving through and the ocean is over down there? That's a marine terrace. Those up, I guess that's kind of north of Big Sur, where these areas are raised, and there's a slight slope up to the hill, up to the mountain base, but it's not terribly steep. So those are marine terraces. So that's what was happening along the coast then. Even though sea level was generally up, it was fluctuating. Then we come to the Pleistocene, 2.6 to 11,700 years ago. Anybody, when the Pleistocene, does that ring any bells with you? Does it sound like a particular time in history? It's ice ages. It's when the glaciers were omnipresent in North America. Now, the trick is, we think of there was an ice age. Well, it wasn't global. Not every place was getting glaciers. North America had glaciers, both what we call alpine glaciers in the mountains, but to our east, we had continental glaciers coming from Canada and extending as far south as Kansas. We find glacial sediments in Kansas from this era. So, epoch, excuse me, let me use the right term. So we had these masses of ice. But the thing is, those periods came and went. We had interglacials. So it would be very glacially, and then it would warm up, and then the glaciers would come back. And it would warm up, and the glaciers would come back. And if you've been up in the Sierra, up just north of June Lake, you may have seen the features that are like coming out of they're moraines. They're the right and left side of the glaciers as the glaciers come out and push all that debris. Well, and there are places up there where they cross over each other. The old ones are on the bottom, and then there were new ones hundreds of thousands of years later. So we see that these glacial periods came and went, which affected both temperature and sea level. And in Southern California, sea level dropped as much as 390 feet. The Long Beach Aquarium has a great exhibit on that. So we know that there have been all these huge regional changes, which explains what we have on our ground, right? We've got the bedrock down deep, but what do we see on the surface and where do those fossils come from? Now, a little bit about our regional geologic setting. We are in what we call the transverse ranges. And I apologize for not bringing one, but if you've seen a map of California and you know the Sierra Nevada, you will notice that most of our major mountain ranges run northeast to southwest. They're northeast, north-south generally. The Sierra, those other ones up north. But we have some differences here. Oh, the San Bernardinos. San Bernardinos run north-south. Let's get a little more close. But we have these transverse ranges in California that are oriented east-west, almost perpendicular to the main ranges. So what happened here? Well, going back in tectonic history, when the Pacific plate, I'll back up a little bit. The Pacific plate is the Pacific Ocean, all that basalt and stuff, but it's covered, right, with sediment. We are on the North American, no, let me rephrase that. We are not on the North American plate. The North American plate is what we think of as North America. Before 30 million years ago, the Pacific plate, which would, if you're looking at a map, it's over here, the Pacific plate was being subducted or shoved under North America. Well, when that happens, that's obviously a lot of pressure. But there's also material being scraped off the ocean. I refer to that as the two brownie problem. These are both trays of brownies with frosting, right? And you do this with one of them, now you got frosting stuck all over this one. We live on the brownie frosting. We live on the part of North America that got scraped off when the Pacific plate was subducted. But that's a lot of pressure, and part of that energy was it rotated, it brought this land ashore, right, this ocean material, but it rotated clockwise. So we now have these mountain ranges that are the edges of this shoved up land that are perpendicular to the rest of the mountains. So, and this is a fairly recent observation, and I'm sorry, in the 80s. It was all very exciting. That's still recent to me. So the idea that this was happening was all very exciting. And that frosting thing stopped about 30 million years ago, and we'll talk about the San Andreas Fault, but that's when the San Andreas Fault picked up its energy. So we've got the transverse ranges. The Soledad Basin, now I see it called the Soledad Basin, the Santa Clarita Valley, there's a lot of names. But we think of it structurally as this is a big basin, and it's bounded by the San Gabriel Mountains on the east-southeast, and the Sierra Pelonas on the north-northwest. And the Sierra Pelona are just this side of the San Andreas Fault. So the trick here is, if you are on this side of the San Andreas Fault, you're on the Pacific plate. You are not on the North American plate. And I always tease, I do tours for buses of primarily very wealthy seniors, and I say, but you may have noticed your feet aren't wet. Well, that's because we're living on that brownie frosting kind of thing, that wedge that was smushed aside. But we do not live on the North American plate. We live on the Pacific plate, atop the material that was scraped off the ocean floor, and then 30 million plus years worth of sediment washing onto it. So the basin, though, is so we're this side of it, so that tells us we're all part of that. Our valley floor, the basin floor, is filled with alluvium, which are sediments primarily borne by water that were weathered out of those ranges. And I know weathering's covered in that material, but basically weathering means the weather acted on it. Water is the number one weathering agent in the world. That's true here. It's true in the Sahara Desert. It's true in the Pacific Northwest rainforests. Water does the most work. Wind varies, right? And if you have a lot of wind in the desert, then it's doing more work, but water's still the biggie. And so these sediments that have been weathered out of these ranges on all our sides have moved down the steep canyons. And I apologize, it's out of point, but that's been going on since 30 million years ago. I think I can fix that, can't I? Nope, guess I can't, sorry. 30 million years ago to about 1.8 million years ago. That's when the main, now it still happens, right? Every time it rains, we see debris flows, mudslides, material coming down the slopes. But the most of it happened some millions of years ago. So that's our surroundings and our valley floor. Now a little bit about those surrounding mountains, right? What ended up in the valley floor that came from the mountains? Well, the San Gabriel Mountains, first off, they're the biggest baddie ones, right? They're just over, I'm pointing yonder in the room. They are primarily plutonic granites. In other words, intrusive igneous rock that rose up over time through the surface and were emplaced as granitic rocks. Again, that broad category. And metasedimentary rocks. A metasedimentary rock is a metamorphosed, or in the process of metamorphosis, sedimentary rocks. There were sedimentary rocks because just like everywhere, those plutonic granites eventually are exposed, right? Weathering takes the surface off. We can see the granite. The weather now works. First off, there's whatever was on the surface becoming sediment, but now it's working on the granite itself. So we have these sediments. And then there's heat and pressure because the San Gabriels are still active. I'll get to that. Something kind of cool, there are anorthosite deposits in the core of the San Gabriel Mountains. Anorthosite is one of the primary moon rocks. The theory behind that, this is an extra little side trip here, there's a lot of questions and a generally agreed upon decision about how the moon formed. Well, the moon got hit by something. An asteroid hit the moon, sent it this blob. It hit Earth and we traded some information. We swapped cooties. So we find minerals from Earth, or elements from Earth, on the moon, and we find moon material in places on Earth because we just kind of hit each other, pieces came off, and then when the moon spun out, it got caught by our gravitational field and started orbiting us. So this anorthosite's kind of a cool thing. To be honest, when you go there, you're like, wow. But mentally it's wow. Visually it's like meh, but it's pretty cool to see. And of course the mountains formed about 12 million years ago. So they were formed by this thing, but there's also fault activity. So what's happened is it's being uplifted. It's being continually uplifted. Over the last 3 million years, it's given us extremely steep slopes, right? Particularly, I would say, on the south side, that we have these very steep slopes, 65 to 70% grade, very steep, but they're still moving, they're still rising. What's happening is, remember I talked about that rotating part of the basin? Well, things are still moving. The basin continues to rotate. We still have pressure now along the San Andreas Fault throughout most of it, but pushing North America from the Pacific Plate. And so the mountains continue to rise at a rate of about 1.9 to 2 millimeters a year, which ain't squat unless you're a few million years old. Now the trick is, though, of course, the mountains are rising, usually in earthquakes, which fortunately through our lifespans we don't see a lot of, but also there's weathering going on. So almost as fast as they're being raised, they're being eroded from the top. So it's not like you're going to come back in 3 million years and go, oh my God, they're absolutely huge, because they've been being eroded. And at this current rate, and again, it changes based on climate, at 0.35 millimeters a year being eroded. Now let me say, 200 years ago, the environment in Southern California was much wetter. And so is that where we're headed again? Could be. But the fact is, prior to human intervention and activity, the climate was I said 200 years, I meant 2000. The climate was much wetter in Southern California. So that could have resulted in increased deposition then, but currently we're doing about 0.35 millimeters. So that's a lot of material headed down the slopes. And while it's not our side of the mountain, if you've ever driven along the 15 to go on up the pass, like you're going to Victorville, you wouldn't go to Vegas, right? Victorville. You notice they're building all these homes on those big triangles. Those are alluvial fans. Alluvial fans are the material that come down the mountain and they form. So if I'm a river channel and I'm full of gunk, I come down and I fan out. So all that material, and it's sloping, right? Because I'm not the flat ground yet. And they're building all these homes on there. So that's a whole other field trip that's kind of fun to look at. On this side, for whatever reason, we do not have as many alluvial fans. However, out towards Acton, we do have some, where it seems like this is where the San Gabriel steps, it goes back farther. It steps right back there. Then we can see some fans on the peaks back there. But along here, we don't have as many, which may be indeed in part because of this basin and the river processes that have been happening in the base of it. But we don't have a lot of those, so that's just, I think that's from the south side, sorry. The Sierra Pelona Mountains, which are to our northwest, primarily blue, and that wasn't supposed to have a dot there, a blue-gray Pelona schist. Pelona place. Schist. Schist is a meta-intrusive rock. Schist, there are ranges of metamorphosis. So we start with a piece of granite, and it undergoes heat and pressure, and it can become a schist. Now, a schist is fun. They're very shiny. They look like they're platy. Have you ever seen rocks like that? They're very shiny, silvery color, and they're platy. That is a schist. If you keep the heat and pressure up long enough, you get a gneiss. And a gneiss are the black and white striped rocks. And we'll talk about those later when we see them outside. Yes?
Just in case people don't know, the Sierra Pelonas are basically to the north of us from Saugus north. So it's bound
Thank you.
with like Saugus to the south. And then you have, it's north of Agua Dulce, north of Acton, and west and south of Lancaster, and south of Green Valley, Lake Elizabeth, and then you have Castaic and the five to the west.
Thank you.
That's the Sierra Pelona.
Right. So when you're driving to Palmcaster, as I call it, because they've merged. Right? Remember when there was Palmdale and then there was Lancaster? It's now Palmcaster. And you go over those hills, it's a low pass at the far end of the Sierra Pelona. And then if you look off to your left, then you do see the hills extend. Quartz Hills out there and some other places on that side. But anyway, the schist consists of metamorphosed marine sediments from over 66 million years ago. So we know they're very old marine sediments deposited. And if we go back a few, when were those marine deposits? There we go. So even before the Miocene, they're very old. So, sorry. Okay. And the whole mountain range is intensely folded. Now, the San Gabriels are eroded, right? They're weathered, they're ragged looking, they're rising, so they're still sharp, because that's the way you can tell how old a mountain range is. If the points are pointy or the points dull, think about the Appalachians. They're these rolled little hills. It's because they're so old, they got worn down. They may once have looked like the Sierra Nevada, but they're old and they've been worn down. Some of us can relate. But the San Gabriel is still, because it's rising, it's still young enough. So, but what we see in the Sierra Pelona are more rounded slopes because of folding. And it's got the San Andreas on one side and the San Gabriel on the other pushing on them. And again, even though they are faults that are supposed to be going like this, lateral faults, and I'll explain that in a minute. Lateral faults, there's pressure. And the whole Sierra Pelona mountain range is what we call a plunging anticline. Now, an anticline is rock that goes up like this. I say, remember an anticline because it's shaped like an A. So it's a compressional feature, right? There's been compression. And just like, I could take that piece of paper and wrinkle it up. It works on the hallway with a carpet, right? You shuffle your feet and it goes up and down. The up part is an anticline. Often they have partners of synclines that go down. Anticlines make an A shape, synclines are sinking. But this is a plunging anticline, and by that it means it's not straight, it means it's plunging to one side, and that it's steeper on our side, on the southern slopes. So again, if you look at the Sierra Pelona, you see some fairly steep peaks. You go over to whatever I called it, Palmcaster, and you look to your left, they look a more gentle slope, right? So that's because this anticline is tilted from the pressure that was exerted on it. Now, I just want to say, I don't know how much you guys have talked in the past, or it was in the book, about faults. So forgive me for not having a slide on this, and I had thought of it and forgot. There are four categories of faults. The first is what we think of as a normal fault. And forgive me, I'm blinding myself, but this step right here, that's a normal fault. This step has been raised up relative to the floor you all have your feet on. A normal fault is, again, compressional, something pushed. Obviously, the contractors were lazy, and they just put pressure on both sides of this area and made this step. But if you see in nature a normal fault, it means that one side has broken up on some sort of fault. Now, let me say, a fault is simply a crack in the Earth's surface or lithosphere. That fault could be the length of this stage, or it could be the San Andreas Fault. Length varies on the amount of pressure and the geology of the area and all kinds of things. But when I say fault, don't think I'm only talking about these biggies. There are little faults, and you might be driving along the road and see some rock that's offset, the layer sediment. That's a fault. It's just not a grand fault. So a normal fault is compressional, and one goes up over the other, right? You're pushing, and one goes up. That's normal. Reverse is the opposite, and that happens, again, when they're pushing and one drops down relative to the other. So it's kind of the same, it's just a different phenomenon. Reverse is that the one in motion went down. But a relation to those is what we call a thrust fault. And a thrust fault is when not only does this happen, but it keeps going, and this goes up and over this bottom one. Not just making a cliff, right? We have a cliff here, but once it's gone over, it rides over. Thrust faults in the LA basin and surrounding area were suddenly hot topic in the early 80s. At first, we called them listric faults because they were very shallow. We're used to thinking of an earthquake fault as going deep into the earth, whereas these faults seem to go just fairly shallow. Like here's the mountain range, and the fault came and it went like this. Well, since then, it's been redefined and better understood that it's a thrust fault and that this one is trying to go up and over the mountains. 1994. Most of you are going to remember 94. I know it was a lot of damage out here. In 94, what's happening is the San Fernando Valley is attempting to go up and over the Santa Monica and Santa Susana Mountains. It's being compressionally pushed up and over. That's why Santa Monica experienced so much damage in that quake. Now, you may not have been aware of this because you were living someplace where it was bad. I was living in Long Beach where it was disturbing, but damage, not a problem. What had happened is that energy, right? So here's the Santa Monica Mountains, and the things trying to go up and over, the energy went right through the Santa Monica Mountains and damaged a lot of Santa Monica. But they weren't getting as much attention because it wasn't as devastating in the valley. And kind of the news didn't even pick on it for a number of hours. The Santa Monica had a lot of trouble too. And again, it was because that energy just traveled right through the mountains. It's a thrust fault trying to go up and over. So, and it happens deep, but it's an issue. So that's a third kind of fault. And again, from my education, my geologic education started in 1975, this is new cool stuff, whereas today's students are like, But anyway, and then the one that bothers us the most in Southern California is what we call a strike-slip lateral fault. And what this means is that two pieces of the earth are moving against each other. Our history is that the San Andreas Fault started moving in this way about 30 million years ago. Before that, we still had subduction going, right? So North America, pardon me, I'm backwards. North America, the Pacific Ocean going down. And due to some complexities of the physics of plate motion, it switched to being this lateral fault motion. Now, just as an aside, we worry a lot about Northern California, Oregon, Washington, and the Cascadia zone. Have you heard of that? The earthquake. It's still subducting. So they got other problems up there. They have 3 faults meeting, and it's subducting, and it's appears to be a greater risk. But anyway, so here we have this sliding function. So now y'all are going to participate. You don't have to get up or do anything. So y'all are North America. You all are the Pacific Plate. This is called a right lateral strike slip fault, which means, let's take those words, lateral meaning which direction does it slide? Strike slip. Well, slip's pretty obvious. Strike means what angle is it going at? Is it headed, like, is it for directionally, but also the underground, is the fault going like this? You know, is that a straight line down or does it go at an angle? So that's the word strike. So we call ours, what we have here is a right lateral strike slip fault. So this is the San Andreas Fault down the aisle, and we have an earthquake. And you guys move up a row. And you guys appear to move back a row. So now you're looking, where are they? Did they move to your right or your left? Right? Well, you moved forward. Okay, you got y'all. You moved up. You moved this way, and they moved that way, it appears. Which way did they move, right or left?
Who's right?
To your right or left?
Right.
They moved right.
Yeah.
They moved this way. Was that to your right or left? No. They moved to your right. They moved to your right. She's not the only one looking confused. So now look at him, and he moves, their entire row moved up here. They moved to your right. Does that make sense? I'll throw her around the Rock Club meeting tonight, no problem. Anyway, so that's right lateral. Right lateral. So you move in relation to the other side. Now, in reality, who moved? It's irrelevant. It's irrelevant which of you actually moved, but relative to one another, somebody moved. In California, chances are good that it's the Pacific side that's actually doing the moving. The North American plate's kind of lackadaisical and it's like we're good. But the Pacific plate's like, no, we're headed northwest. So we continue to have these faults moving the Pacific plate side, our side of the San Andreas, to the northwest. It's going to be 14,700,000 years before we can wave at people in San Francisco, so don't worry. My students have to figure that out. Yeah, I'm sorry.
However, you have a really interesting example of this, which would be the Carrizo Plain, which is north of, like Pine Mountain.
Yeah.
In that range.
West of Bakersfield, west of Taft, actually.
And then you have Pinnacles further south, and they find almost like half of rocks in one and the other. The same rocks that you could see where they
Yeah, actually, Pinnacles has been offset. The Pinnacles National Park to the north, up around Hollister, versus, and I can't think of the name of the town on the way out to Bakersfield I apologize. So if you were driving up the pass and you turned right, like you're going to go out to Mojave that way, south of Taft, this side of, no, the Pinnacles are up north. The Pinnacles National Park is to the north. But the same rocks are on the other side of the San Andreas Fault, down near, I'm blanking, I apologize. It's got a weird name. Yeah, this side of Palmcaster. The point being, they're about 200 plus miles apart when it's run rock formation. It's the same rock, south of Gorman, southeast of Gorman, and I apologize. I have friends who lived there, and I'm... Neenok! Thank you. Imagine not being able to remember that name. Yeah, Neenok rocks are the same rocks as at Pinnacles. But over the 200 and something million years, or 30 million years, 200 and something feet, the Pinnacles National Park has said later days and moved northwest. Neenok is right where it was, but it's the same rock. So thank you, yeah. And then obviously I mentioned right lateral, which is the predominant northwest, southeast trend we have in this state. But we also have east-west trending ones, which are left lateral. So now when we have an earthquake, y'all are going to move forward or backwards to her left. And now when you look over there, it looks like she moved to your left. Now the left lateral faults are, the Garlock is the main one we know about. It's not far from us. If you've ever driven up 14 to 395 and gone through Red Rock, you've crossed the Garlock. And that's a big fault. The problem is it gets a little messy because it runs into the San Andreas. And so that's where the San Andreas takes its big bend and curves and pressure can build up. It's a whole nother topic. But the idea is that the reason we had an earthquake up there in 1857 was because the faults coming along from, again, I'm trying to be a map, coming along from Southern California, and it goes up and it curves. So all this material that's trying to head northwest is going, excuse me, you're in my way. And so we have more earthquake risk up there. So yes, I personify all rocks. My first geology teacher called every rock was Stanley, and they all had behaviors. So it was wonderful. Anyway, so we've got the Sierra Pelonas. Now our valley, let's talk about where we are. It first took form in the Pliocene as a shallow sea. Remember we talked about most of everything was still covered with water. And the sediments from the mountains at that point were washing offshore for about 30 million years. Of course, with the oldest ones on the bottom and the younger ones on the top. It was what we call a shallow offshore environment, not 1,000 feet deep. So there were gastropods, different shellfish, different cetaceans, and saltwater plants. And when they passed on, they left their fossilized remains. Now, vegetation doesn't leave a solid remain, but it leaves sometimes a cast or a print where we can see the leaves. And if any of you have ever found those, I'm incredibly envious. I have not. But we find bones and shells, and I have friends who lived out in Castaic, and that was when they were kids. The thing was going out in the channel to pick up shells. And this is why. Now, the water was fairly warm, but we're not talking about the tropics. We didn't have beautiful saltwater fish. It was still a fairly cooler environment. But then later, during the Pleistocene, right, so that's during the Ice Age, the coast ranges were uplifted. Again, we're talking about motion on the San Andreas Fault and all sorts of things happening there. But while that was happening, so we're getting a mountain coastal range, again, running primarily northwest, southeast, and our basin was broader and shallower. We hadn't really yet had the down cutting that occurs from flowing water, right? Water makes channels deeper, and the mountains weren't still quite as high around us. But runoff from the coast ranges coming this direction, coming sort of east, left behind stream terrace and fluvial deposits. Fluvial is the fancy word for stream. Stream terraces and fluvial deposits atop the sediments. So when I say a terrace, what I mean is, so we've got a stream flowing in this room. The whole thing's it's going from left to right or right to left, depending on where you are. The stream's flowing. And over time, it downcuts, right? Because flowing water is moving material. But let's say 200 years ago, the stream was from that wall to this wall. And now, it's only from here to that wall because it's gotten narrower. Well, actually, there's stairs back there. From here to the bottom of those stairs. This becomes a stream terrace. The higher area alongside of the active channel is a stream terrace. And that is just an indication of prior river height. The area, though, because the water is probably not running all the way from the bottom of this terrace to the bottom of that terrace. So in that area, we call that whole area the floodplain. And the floodplain is where water may flow either in an active channel or go over the edges in an active fashion, not flooding. There are many who support the idea that a river terrace will never flood. I am not among them, but famous fluvial geomorphologists are. Had many an argument in the field with my friend and advisor. But so the floodplain is all this lower area where you're sitting. And again, the active channel, it might be a dry stream, right? The Santa Clara River half the time is dead dry. But the floodplain is the entire width of that channel. I foolishly live a mere 14 feet above elevation among the center of that channel. So I live on a terrace. I love showing my students that because I go, what kind of idiot would live here? They all laugh. I go, I do. When I moved to this area, I had to pick between fire and flood. Flood gives you warning. Fire is a burning roof, so I picked flood. But anyway, the point is that the floodplain is the area that may regularly flood. And it's outside the active channel, and there are things you can see about it, and if we look at the pictures or have a chance to go outside, I can point those out. But so that's what was going on in this valley. It was down cutting, and of course changing path and all sorts of things along the way. Okay, let's talk about the faults, right? Because we've talked about the mountain ranges, which I've said have been risen, right, in many cases by the faults. Our first one, the San Gabriel, the big bad one, the daddy of the valley. It's 15 to 10 million years old. Now, when I say that, it's weird because the San Gabriels have been uplifting because of pressure, but it's a strike-slip fault now, too. It, too, has evolved. So it's been pushed up by pressure, presumably along normal fault lines where it rose up, but also in the last 10 to 15 million years, it's become right lateral strike-slip. So we've got that, right? So if you look at the San Gabriels, if we have a big earthquake, it's south of us, southwest of us. We're going to go by, and it's going to look like it's going that to us, and we're going to look like we're going to the right. Now, when I put north with concordant normal faulting, it's a lot of pressure. That's a lot of land. When we talk about a strike-slip fault, chances are very, very high there is going to be some vertical offset. I'm pushing as hard as I can against my hands, and when they finally slip, this one went a little higher, right? So, right, I've got one side of the fault, the other side of the fault. I'm pushing, and I'm going to slide, but when it goes, one goes up. And so we often have normal faulting, one side going up relative to the other with a strike-slip fault. So that is probably why I believe, from what I read, that the San Gabriels are currently rising as part of that pressure. Now, the Placerita fault isn't its own fault in a sense. It's what we call a splay of a larger fault. Now, the trick is when we think of a fault, any fault, we kind of think about a single line in space. Actually, it's a fault zone. There may be, and likely is, one primary line of motion where the most of it's happening. But parallel or subparallel are other faults in line with that are adding to that movement. And those are called splays. Sometimes the splays are very small and relatively unidentifiable. Other times they're big, like the Placerita fault. So the Placerita fault runs subparallel and joins up with the San Gabriel fault. It travels through our valley in a different place than the San Gabriel does, but they're related. So it's just a smaller subset. But let's look at this. So try how to figure this out. Okay. So we're on. So in this case, you guys are a fault moving this way, right? So you're on land going that way. But here, you are too. You're going that way, but you're on a different fault. So if you're both going the same direction, everything's good. But sometimes they end up with, and I'm sorry there's no board for me to do this on, but if you've got right lateral here and left lateral here. And then I have right lateral here and left lateral here. Here we had right, and here we have right, well, I'm sorry, I said this, so right going down, and this was right up, right down. Here we have right up. When they both move, they pull apart, and they can create a basin. In some places, they move together because they're both moving towards the same direction, and they create a ridge, a pressure ridge. It's the same fault, but it's a pressure ridge. And there's a lot of these on the east side of the San Gabriels out in Palmcaster, but then that's because of pressure. So we end up with different topography in some places because of these parallel faults. So it's entirely possible that some of the hills between when we're along the creek and we think this is the Placerita fault and the San Gabriel's over there, that may be some pressure ridge that they've been pushing, working against each other in essence, even though they're trying to go the same way. So that's our Placerita fault. The San Andreas fault, as I mentioned, is about 30 million years old. That's when they got tired of subducting and all these complex geometric issues took place. And now we're a right lateral strike slip faulting, trending northwest, southeast. So we here on the Pacific Plate are headed northwest, and theoretically northwest is hanging, the North American Plate is heading southeast. In reality, they're just holding steady. They're not going anywhere. Now, who knows what will happen in a few million years? North America may take off running. Sort of as an aside about plate motion, think about India. India has been running into Asia, the Indian subcontinent, has been running into Asia for over 225 million years at a rate faster than any recorded plate motion on Earth. And it's still pushing. That's why we have all those A, high mountains known as the Himalayas. It's a big wrinkle. And B, excuse me, there's lots of earthquakes, right? Because India, so that sort of stuff still happens where plates can move quickly. Another issue, if any of you happen to watch the earthquake news, like Vanuatu and some other areas in the South Pacific having lots of earthquakes, that's because Australia has decided, the plate of Australia has decided it needs to move along. And it's moving like 6 feet a year. But of course, it's not like somebody moved out of their way. So they're having all these earthquakes. So the Earth is constantly moving around like that. So 30 million years ago really is fairly like the day before yesterday. And then the Sierra Pelona Fault, again, the one off at the base, it's just this side of the San Andreas, and it is a normal fault. It's something, it's only about 25 million years old, probably caused as a response to the San Andreas Fault. So the San Andreas Fault's moving, and the side towards the Sierra Pelona is headed northwest, and that's going to put pressure on existing landscape. So now it's a normal fault, primarily. In other words, the Sierra Pelona are being uplifted, but there is also some northwest-southeast motion because it's going along with our Pacific Plate motion, right? It's still on that. So the Sierra Pelona mountain range is caught between one part of the San Andreas trying to move north and the opposite side of the Sierra Pelona. So that's another reason for all those folds and things. So it's, again, 25 million years old, could be argued to be a splay of the San Andreas, but it's really its own independent thing because it moves differently. Yes?
Yeah, so we know that the San Andreas Fault has a few little glitches, those little bends. And we know even the San Gabriel Fault, much less than the San Andreas Fault. It's pretty straight. But the Placerita Fault coming off of it is wonky.
Yes, that is entirely possibly a part of the fact of the geology. It's not as big a fault, and so the harder rocks may have sort of deterred it a bit. We do have the underlying granite in the area, and then what we see of the fault, and we'll show you this map at break, you can come and take a look. The Placerita Canyon Fault is in dotted lines because they're not quite sure. They know there's a fault here, but exactly where it goes. And so that's part of it. We assume, oh, the fault goes that way because that's where the channel goes. But maybe that's where the channel goes because the rock was softer and that the fault actually goes through the hard rock on the right of the channel. Oftentimes we see streams in fault because it's weaker material, right? You have all this material pushing on each other, it wears it down. We call it fault gouge. And because it gouges away, and then it flows away, and you have a river channel. So it may be that we're looking at it backwards there, because we don't know. And I don't know if anyone's come out here in recent years. I couldn't find anything with a gravity survey machine. You'd have to go up the hills with the gravity thing. It'd be a nightmare. Satellites are getting better at that. We may well know before too long. But we don't know exactly where the fault goes. So it may be that we're a little misled by its curvature because of the solid rock diverting the stream. And we think, oh, stream fault. There's also something else we can see, like on a hillside, if you look up a hillside, and you see what we call saddles, where there's a ridge going up, but it has a divot in it. That we call a saddle, and that may reflect a fault higher up a slope. Because for some reason, faults seem to move up slope over time. It's just a progression that these strike-slip faults move up slope. And so that we sometimes see, or it may be a splay, a parallel fault. So we see those. Thank you, Sandra. Good point. Okay, our canyon. And this is not the greatest diagram, but it's the best aerial I could find. The canyon runs east-west, formed along the Placerita Fault where bedrock has been fractured, and sediments eroded by the water flowing currently seasonally through Placerita Canyon. And I say in its fluvial predecessors because before it was Placerita Creek, it may have been a raging torrent, right? It was a wetter climate. We don't exactly know. And if we do, those papers were above my pay grade because I was looking up papers. But it appears. So here we've got the canyon, you've got the 14, the road coming up, and then the canyon's outlined and and then the waterfall. Just kind of though giving you, this was a hike somebody did in 2009, but it's a good outline and we can see our slopes and how we come off the San Gabriels over there and come back down. So it's kind of a good overhead. It was hard to find, I don't own a drone, it was hard to find a good overhead. But it's just that it does run primarily along the Placerita Fault, which is uncertain as to its exact location, but we know that the canyon is there because of the fault and the fault gouge and the erosional processes. So we can trace why it's here to the fault, even though we're not sure which direction on the dotted lines to say. You know, there are places in this country, there's places in Palmcaster where you can stand theoretically with 1 foot, just like in Iceland, 1 foot on one plate and one on the other. But it's not the main fault. I mean, I take people out there and the red color is one plate and the white color is another, but that doesn't mean that 40 feet that way there's not more of the red color. So it's just their splays. So we don't exactly know. But technically, in this, theoretically, let's put it that way, theoretically in this valley, if you cross the creek, you may be getting closer to the North American plate. You may actually be on a little part of it, but the official boundary is the San Andreas. Now, what's gone on around here sort of historically too? Black gold, right? Texas tea. It tells me how old I am. Ancient marine organic material. So live organic materials buried, they create heat and pressure over millions, or they are subjected to heat and pressure, and they create heat and pressure over years, and in some cases turn to petroleum products. This is where I have to disabuse everyone. It's not the dinosaurs. It wasn't ever the dinosaurs. Sinclair's just using the logo. It's not the dinosaurs. It's vegetation and some other organic material. So in this case, primarily vegetation, but also other organic critters. And so that's what becomes petroleum. Now, all these complex folds and things we have in our sedimentary rock trapped oil and gas. Fortunately for us here, it appears to be oil. We all know about the gas fields to the west, right? And the topa-topas, not so good with all the leaking natural gas. We have oil, and so that's a good thing. And it was obviously a much better thing economically some years ago. In some places, the way it was discovered is oil actually seeped to the surface. Now, it did not take a shotgun like Jed, thank you. I was like, it's not Ethro. Jed shooting up the oil. But it just comes up on its own in the sandstones. And to be honest, if you drive west on the 126 and pull over and look up into the hills back there, you can see black spots. There is still oil seeping out of the sandstones. Huh? Is there some here? Okay. Well, what I was going to see, all I know about here is where white oil, or actually transparent oil, came to the surface. It was filtered through that metamorphosed schist, and the heavy hydrocarbons were filtered out. It's found off the canyon trail, so you guys it's referred to as a bubbling pool of white oil. I left out bubbling because that was pretty dated. But that's unique. That, in the material I found, 2 sites, the only place it's ever been found. So we're very unique in that respect. Drilling started here back in 1859 in Pico Canyon, close by. The Pioneer Oil Refinery, right, 1859, same area, up in Newhall, and it was the first one in the valley. And today, as we know, commercial drilling continues around this area. The Disney property, right, has a lot of wells on it up the hills. There had been a fire and all the signage blew down, and so we went up there, we didn't know. There were no fences, there was nothing, and a Disney guy came down and threatened us. We're like, yeah, put up a sign if you don't want us here. But we were getting near the wells, so we figured, okay, that's private property, we're not going over there. But anyway, so it's still going on, but obviously if you've been here any period of time, it's much less. I remember, as I said, I had no idea where this part of the world was, and on the rare occasions in the early 80s driving through to go up to Mammoth or whatever, there were a lot more on the hills. Of course, I always wondered why anyone would live out here, but now I know it's a beautiful place. So that was a little bit of our oil history, but we also have the gold history. And first, let me back up, because I didn't write why we have gold out here. Because often metamorphosis, right, the change in rocks, is brought about by geothermal or hydrothermal, hot water materials flowing through the cracks and fissures. The term solid rock is a misnomer. There is really very rare that you're going to find solid rock. They all have even microscopic fissures and cracks in them. So this hydrothermally heated water, and it doesn't take a volcano to do that because it's warmer grade, right? That's how we have geothermally heated houses now. So water that's heated a little bit and has these minerals, particularly gold element in it, floats through, and what happens, it gets in this crack and the water evaporates, leaving behind the mineral deposits. So that's the same way we find silver and a lot of other minerals. So that's why it's here. Granite is not usually a good place to find gold. It's not unheard of, and it would only probably take place if there had been this hydrothermal alteration with the material coming through. But again, metamorphosed rocks, where they're generating heat and pressure, is going to have warmer water, so that's probably where the gold is coming from here. And I'm sure you guys all know the charming story about Francisco Lopez having a nap on his, the way I heard it was like, because it was cousin's ranch, and he was sitting under a tree and pulled out the onion, and there was gold flecks on it, whatever. Well, his family later claimed that he was a trained mineralogist and that he was looking for gold. And he did find it, but probably not on an onion, but in placer deposits in the stream channel. Wait, Placerita. There's a link, right? So the placer deposits in this area, and again, what are placer deposits? Placer deposits are bits of, in this case, gold ore that come downstream in the water flow and settle on the bottom. This is a kind of place where you go gold panning. You don't bring out your pickaxe and start digging away. You're going to be picking up stuff that's in the stream channel, the pans. Anybody ever done that? Gone gold panning? I find it incredibly frustrating, but I also know people who've made money on it. So I commend those of you with the patience to do that. So he did find some gold in the stream channel, and he had actually already found it in Pico Canyon or Piru Creek, or there's all these places. He was working the area. But the gold mining started, and I think it was Fremont who was coming, I can't remember now, one of the fellows who built gold facilities up north actually came through and learned things from the Lopez family about how to process gold before they went up north when they found gold that in 1849, the big gold rush. We had a mini gold rush here. And gold mining continued actively until the mid-40s. And a little side note, one of the mines out beyond Acton, Red Rover Mine, I believe it's that one, that was operated by a wealthy Californian who was a friend of FDR's. And finally, FDR had to say, yeah, we've outlawed that. You need to stop. Because he was still doing it. So that was one of the last mines we had actively mining out there. But I have friends who go out after a big rain to collect float out there, out near Acton. And they collect little bits. And it's more a fun activity than, a prospect of earning money. But there is still gold coming down the hills. And float simply means that the rain washed it out and it's on the surface. You don't have to dig for it at all, nor is it in an active channel. So we did have gold here. Let me see what I go to next. Why don't we take a break now? Because then I've only got 5 more of these slides. Yeah.
If you could explain simply, how did Vasquez rocks form?
Certainly. Vasquez rocks are sediments from the San Gabriels that wash down, and they are along one fault, particularly the White Wolf. When the White Wolf caused a big earthquake in Bakersfield last century or earlier this century, I forgot what century we're in, last century or the one before it, and it's compression. And so they were uplifted that way and then eroded. And if you may know, for those who've been out there, the name of Vasquez rocks is because of the Mexican bandit Tiburcio Vasquez and his guys hung out there and hid for over 2 years while the law looked for them. I have a sense that if they'd really worked, they'd have found them, but it's a pretty complex environment. They probably went, nah, never mind. But yeah, so that it's just uplift, and it shows in the little visitor center there, you can move the fault and see how it happened. But it is this side of the San Andreas Fault, so there is pressure from the San Andreas, but it was actually more local faulting that caused that specific uplift and commercial bounty. Every third Tuesday of the month at 7 p.m. Normally we meet in the Greenbrier Mobile Home Clubhouse, which is there on Soledad, almost across from the old raceway, actually closer to being across from the miniature golf place. Currently we're meeting in the bar at the bowling alley, the Santa Clarita Bowl, because, Santa Clarita Lane, excuse me, our clubhouse flooded. But apparently the repairs are happening fairly quickly, so we hope within a month or two that we will no longer be in the, but they're nice, they're letting us use it for free. Last month the club bought pizza and soda, this month I'm including everyone else too, and since it's my birthday I'm having a beer. But anyway, so we meet, we have old business and new business, old business being new members, past field trip review, and then we do a field trip. We try it once a month, usually the third Saturday. This month it's going to be Sunday, and we go someplace within a couple-hour drive most of the time and spend the day collecting. Next Sunday, well, first off, our meeting is tonight, 7 p.m., Santa Clarita Lanes in the bar. And you can get a soda, and they have good pizza, Vincenzo's Pizza. And then next Sunday, we're taking a trip out to our claim, which is a travertine claim. And travertine, as many of you know, is a form of calcium carbonate that is formed in sort of horizontal layers. It's very pretty. If you ever went to Mexico and bought Mexican onyx, you bought travertine. And so which is fine as long as you don't pour vinegar or hydrochloric acid in it, you're fine. So anyway, we're going out to our mine partly to collect and partly to clean up because it's an open area where people can come, and they're not all as neat as we are. So anyway, if you're interested, please, come on out. We have a website. We have a Facebook page. You can get information on those. Again, Sierra Pelona Rock Club, SPRC.
She's our president.
And as a side to that, Glenda brought up, she has a little bag of shark teeth. How many of you ever heard of Shark Tooth Hill? Shark Tooth, for those of you who haven't, Shark Tooth Hill is up east of Bakersfield a little bit. It's private property where there are gazillions, and she's showing them, of shark teeth, some vertebrae, dolphin teeth, a variety of marine fossils. There's also a lot of cattle fossils that are interesting if you want to. I have a vertebrae at home, it's like this big. But anyway, it costs to go, it's like $60 or something for a day or half a day, but you can sit there in the dirt and play. So first off, I would say that the Rock Club is gone and will always continue to go, but it's also something you can look into on your own. Just look up Shark Tooth Hill, and it's a pretty cool place.
And before you get started, for senior docents, remember we're having, Cindy asked me to remind you, we're having a meeting after docent training regarding some trail issues, and that'll be probably in the building. Okay?
So you don't get to escape, sorry.
You don't get to escape.
Okay, so I just use that as my commercial break. So this is just, I have like 4 slides, not a lot of this, but about what goes on out here now. Well, first off, earthquakes, right? And if you were here in '94, this is particularly high in your consciousness, a little bit of the contemporary history. In 1857 was the Fort Tejon quake, estimated 8.2 magnitude. It was long before Richter was born. And to be fair, we don't even use the Richter scale anymore. He wasn't wrong, but it's more applicable to certain kinds of earthquakes that happen here in Southern California, but it's not universally accepted. So we usually use something called MM, which is moment magnitude, which is a measurement taken more scientifically of the actual magnitude at the moment of rupture. But anyway, the Fort Tejon quake was 200 miles of rupture. And that is the last earthquake of any significance to have taken place on the San Andreas Fault. We all know about 1904, right? And we know about hello, brain. Sorry. No, that wasn't on the San Andreas either. I'm sorry, Fort Tejon. Oh, and then down by the Salton Sea where they're always trying to get our shirts in a knot, and that's where it's going to happen. It could, but the last one was in 16 something. So is it building up and it's coming, or there is some thought there are a number of parallel faults, they call them splay or en echelon, lined up with the San Andreas down there. And one thought down there in southern California is that those smaller faults are taking up the energy, but also it appears that the San Jacinto fault is taking on the responsibility. Down there, that the San Andreas may be going, bro, I'm tired. And the Jacinto's going, okay, we'll take over. So anyway, there hasn't been a major quake. And anybody remember in the early 80s about Parkfield? And the USGS was convinced the big one was going to happen in Parkfield. Parkfield is north of the Bakersfield area around Hollister, sort of up as far as Hollister. And Parkfield's a small town where the fault goes right through town. The bridge is bent. It's really a great field trip place. So they were there. They had millions of dollars in equipment, and nothing happened. So they packed up most of their belongings and went home, hat in hand. There was a near 5.0 a couple years later, but it wasn't the one they had forecast. However, came out of that is that the awareness that common rocks in California include serpentine or serpentinite, which is a product of subduction and all that sort of stuff that happened millions of years ago. Well, over time, that degrades to talc. Talc is slippery. So in places where that has happened, instead of fault pressure building up and breaking, it goes do-do-do-do-do-do-do, and it just creeps along. So the Parkfield region is one where, yes, there can be quakes, but the really mega one probably won't because of the presence of talc. And that would not possibly have been discovered for many more years had they failed at Parkfield. And if you go up there now, there are still buildings with seismometers and things in it. But anyway, so 1857, last quake on the San Andreas. 1893, Pico Canyon, out here off to the west, estimated again 6.0 magnitude. Mentryville was seriously damaged, but there weren't a lot of people out here yet. So there wasn't a lot of damage elsewhere, but a lot of landslides from the rock shaking loose. So that was a regional one. 1952, Arvin Tehachapi, 7.0. Richter was alive and well. He came up with his theory in 34, I think. And it's an anticlinal ridge, right? One of those pushed up wrinkles near Grapevine, but it's on the other side of the hill. So Arvin Tehachapi would be as you're coming down the 5 or the 91, it's over yonder to your right to the east. And that was a big quake. But again, even in the 50s, there were farmers and ranchers out there, certainly, but there weren't any metropolitan, even small areas. So there was damage in Tehachapi, but again, Tehachapi's there because of the train, because of the railroad track. And if the track was, I didn't find anything about the tracks having been damaged, but I'm sure they would have been readily repaired. Then in 1971, which many of us remember, 6:04 a.m., I believe it was, the Sylmore San Fernando, 6.5 magnitude. The epicenter was east of Soledad Canyon Road and Sand Canyon on the Sierra Madre Fault, which again is a little splay of the San Gabriel, so in the San Gabriel Mountains. It had 2 meters of vertical and left lateral offset. So that had a big jump and a switch over. So we all remember perhaps, well, those of us who were around, the rest of you may have read about it, the name of the hospital, help me. Thank you, Olive View Hospital. A Veterans Hospital was pancaked. It pancaked. So there were a lot of deaths and injuries in that area and homes destroyed, et cetera. That was sort of, I'm going to say the first one, right? 1952 wasn't in LA, right? It was north. And here in Santa Clarita, I'm sure you felt it, but the rest of us south were clueless, right? San Fernando Valley and farther south. Sylmar, everybody felt. I know I was in Torrance, and it was a good shaker, and we didn't have to go to school. It was my friend Marinen's birthday, so we got to go play on her birthday. But, you know, that was kind of a big deal because that was the first one we'd really felt. And, of course, 1994, a 6.7 magnitude. Now, we have to remember that magnitudes are not geometric increases. They are logarithmic. So there's like a 30% increase in energy, greater energy with every decimal point up. So that 6.4 to 6.5, pardon me, to 6.7 really is a lot. And I already mentioned it was a blind thrust fault, meaning there's no evidence on the surface. We had no idea. Obviously, an extensive damage to our infrastructure, residences. Many of you may have had damage in your homes. I have friends in the valley who watched their pool do what we call a seiche, which is when the waves go back and forth. Fortunately, they were going to the right and left, not towards their house. I live in Greenbrier Mobile Home Estates down, I already mentioned where that is. A lot of the homes came off their foundations. I've seen video. My house was a triplex because the porch was here and one part of the house was here and the other part of the house was here. And they put it all back together, well, I think. And, but there were homes lost, there were homes burned. I'm sure that happened throughout the country. And we all know about the freeway. And I will not swear to this, but I have been told, first off, backing up, in 71, my cousin was one of the chief traffic architects, whatever, on the bridge system. Lived in Buena Park, had to come flying up here early in the morning. And the story was that it wasn't finished, that if there's part of a bridge here and part of a bridge here and they don't connect, they're not going to move in the same way as two individually. Is that true? I don't know, but it makes some sense. Now in 94, someone I know who took a course from an engineering course at CSUN said that the problem was that on the far side, if you will, the west side, there's that slope, right? That graded slope, which is always, grading is always a risk. So a graded slope, and they put the supports in. So you have a graded slope and they put the supports in like staggered height instead of all to the same length. So when it sheared, they didn't all reach the same depth. They were all the same length going up the hill, so they didn't all reach the same depth, and they sheared. I would not swear to that in court, but that's what I was told by someone who had heard it from an engineering professor. So we've learned a lot, right? We've learned every disaster brings us new knowledge. Natural environments get messed up. There's a lot of landslides. Something else about the 94 quake, there was an outbreak of valley fever after the quake in the San Fernando Valley, as well as this valley, and on up farther north. Well, valley fever is transmitted by little spores that live in the soil, and they're quite happy they're all on their own. But when things start shaking and all that dust rises, the spores were released, and again, there was an outbreak of valley fever. I was told I had valley fever before that, had it. They said, could you have had valley fever? I'm like, yeah, because I have calcified nodules in my lungs, which apparently are residual from valley fever. It's one of those, they look at you and go, could you have had that? I'm like, oh yeah, I've had the bubonic plague. Yeah, Death Valley, don't sleep out. You know, $1.69 is the prescription at CVS, I was fine. But anyway, the point being that valley fever, so we think of things, we're aware of physical damage to infrastructure, to our homes, to our belongings, the upset of our lives. How many of you had to take the train into work every day to get, right, I know a lot of people had to do that, to get out of this valley, to get to work in the San Fernando Valley or beyond, had to take the train every day for a couple years. So Ron is the person who's told me that. So it's definitely upsetting, and unfortunately, there will be another. We don't know where, obviously, we don't know when, but it'll happen. Next, mass movement is the fancy, classy word for landslides. When you hear someone on the media say there was a landslide, they've not really told you a lot. They know that something that was up is now down. But there's all different kinds of landslides. And while we don't need to go into those, what's happened in our valley, they're usually small events, either triggered by saturated hillsides, right? It just gets too muddy to stay up there. Or steeper slopes, whether they're natural or graded. Graded slopes are a big risk. And they happen everywhere. Obviously, earthquakes can do it too. I should have mentioned that. Well, in 1987 through the 90s, I'd never heard about this. You guys aware of Slippery Hills?
Yeah, I live there.
You do? And are you on your way down?
Yeah, eventually.
Okay.
Not in my life.
Golden Valley and Villa Princesa. What's the high school right there? Canyon?
No.
No, Golden Valley. Golden Valley High School. I like my phrase, unwise grading and later saturated slopes, right? So it's up on the hill just off Golden Valley or Villa Princesa, and it's been slipping. There have been a number of events. Nothing too certain. I read something about 3 houses being red tagged at one point.
Oh, yeah,
But-
in fact, in my road, at the end of the little cul-de-sac, there's 3 houses that slipped down. Down below, there's 4 houses that were wiped out. actually a little anecdote, Slippery Hills, I've heard it called, supposedly the indigenous people called it the walking hills.
Oh, wow.
It's been slipping and walking forever.
Oh, I'm sorry, that's marvelous.
Yeah, I was just gonna say walking hills, and then the ones that are over, in Stevenson Ranch by Pico Canyon, were called the Wobbling Mountains. And during the 94 earthquake, I could actually see them doing this.
Wow.
And you could see the dust coming up off of them. And these are, if you could imagine, looking at the hills across the 5 freeway, looking west, southwest, you could see those mountains actually doing that.
Excuse me, I'm taking note of that. Come on. Slippery Hills as Walking Mountain.
You know, walking hills and slippery,
Sorry.
walking hills and wobbling mountains.
Cool.
I think those are too much names.
Technical terms.
You realize my audience is usually 18 to 20-year-olds who can think of anything better to do than being in my class. So, although this semester I have a man older than I who writes poetry as his answers. It's awesome. Yes.
Also, I grew up out here in the late 60s, early 70s. The housing tract that I grew up in off of Via Princesa, right off of Golden Valley. At the bottom of the hill that I grew up on, we lost 3 homes due to poor grading after heavy rain.
Oh.
And we almost lost our backyard pool going down onto Friendly Valley Parkway. That was a big deal
Yeah.
in the 60s.
Yes. Well, because development was still fairly recent out here.
Apia.
Yeah, those 4 houses, those
Yeah.
lots are still in.
Yeah.
Development was new out here, right? So we weren't used to hearing about that. Most of the people lived on the flats or had lived on the hills for a long time. Yeah. Sandra.
When I had moved out here, it was probably around that time, actually before that. I was told not to buy a house there because there was a layer of clay that would cause things to be slippery. You don't want to buy anything, and it was before 87, so.
Yeah, it was the late 60s, it was like 68, 69 on those huge El Nino
Wow,
years.
yeah.
So you can modify that a little bit or add that. It's late 60s where a lot of the big damage happens there.
Well, it was funny because when my parents bought the house, they were told by the contractors and the developers that the whole area to the east of them, which would be where all of Farrell's Ranch is now, would never be developed. It would always be a green belt because the land constantly moved. It was subject to landslides, and now there's thousands.
Organizational memory doesn't exist. Wow. Well, and not that it's in your neighborhood, but I grew up with, you've all probably read about the problems in Palos Verdes, near the Trump Golf Course and all that. Well, first off, that was what you did in high school. I had a car, I had a 68 Mustang, and I was the only one, so we would go, my guy friends would drive, put me in the back seat, and we'd go up and over the road where all the pipelines are on the surface and it's been sliding. Well, it's been sliding for over 15,000 years. I'm always proud to say that the big slide took place 69 years ago today, when overnight they had started cutting into the hillside and left a bit of heavy equipment on the little ledge they created, and it wasn't on the ledge in the morning. So it was already sliding, but that was a memorable day. So my mother celebrated by having me. Anyway, so so it's an ongoing problem. In 2015, you guys probably remember the Vasquez Canyon slump over there on the right, the good picture of the highway. That is, again, a historical slump. And a slump is when we think about how we slump in our chairs, we go like this, right? Well, in this case, the hillside did that. It leaves like a crescent-shaped mark, a cliff up at the top, and then it slides down, and it kind of slides against the grade. The hill is no longer sliding like this, but part of it's going backwards. And it slid down, and it munched out the road. And if you look at the left of that picture, there's more hillside. Well, that's because that hillside used to connect to that hillside. It was a nice solid slope. And they cut the road through, which weakened the support on the higher side. As we refer to it as culling off the toe of a slope, they actually left the toe, they took the main part of the foot out. So, but it's very common, and they'll put up retaining walls. They'll cut the base of a slope off and put up a retaining wall. It's a nice short-term solution. But especially if there's drainage in that slope, it's going to keep pushing. So Vasquez, I love driving through there now and going, yeah, we'll see if this happens again. 2019, above the Trestles community on Soledad, where the railroad track is closer to Soledad, and then there's a housing track going up, and there are other houses above it. So the houses that were above it were all fine and handy until they built the trestles, cut into the slope, and the houses above started to slope. And again, at least 3 homes were red tagged. So I had a student that semester who lived there, and they said their backyard was going away. And then in 2023, and I had not known of this, up there in Skyline Ranch, they had had a small 2.9 earthquake in saturated soil post rain, and homes slid down the hill, 3 homes. I know this is close to where Lisa lives, sort of, up the hill a little bit. You're not that far up, but yeah, and I had not known about that one. That community is beautiful, but I think it amusing that the 55 community is at the top because it's more expensive and better views. Think how much longer it takes to get the ambulance up there. We drove, I went, nope. Yeah, it's like unwise from a social engineering perspective. But, oh, and I'm sorry, on the right, these are images from the trestles. So it's just a little picture of someone's backyard, cracked, there's a nice fissure in the yard, and the wall is heading down slope. So, yes, yeah, that's true. Can I get that bigger? No, I can't. Sorry, yeah. The day we went out, it was fenced off, but for vehicles. They hadn't yet realized what it was going to become. So we were able to walk up and walk around. But yeah, then it became an amusement park, so. Well, flooding, rather timely, and unfortunately today, it's ever present, right? Given the presence of the Santa Clarita River Channel, where I live, and all these streams that flow out of the mountains all around, Placerita Creek is seasonal. And I believe it's probably pretty darn dry in the height of summer, but right now there's earlier this week, there was a pretty good flow, it was last week, pretty good flow going through it. And most of the waterways in this valley are seasonal. But every time there's been a lot of rainfall, there's a risk. For one thing, sometimes a channel can become armored because there hasn't been enough water, and so the water doesn't soak in regularly. It'll work its way down after a while, but if it's a sand or something bottom, it may not absorb the water as quickly. Because right, stream channels aren't just what we see. There's usually water flowing underground in that same area. And so those can overflow. And again, that's why we talked about the floodplains as being areas where you can have damage. And again, the channels here are mostly bordered with boulders, and the channel has everything from coarse sands to boulders. There's not a lot of fine sands. You'll find fine sands in the channels like in little hidden spots, because what it amounts to, so moving water can carry bigger and bigger things, the stronger the force of the water, the volume and the speed. But if the water kind of gets hot in a little turnaround, caught in a turnaround, it can carry really light sediments like fine sands and silts and clays, and they sit there and eventually they can settle to the bottom. So you're going to find some fine sediments in little places that are sort of secluded from the main channel. But the main channel is mostly going to be larger sediments. So I just had a picture of the waterfall, which I have never hiked up to because I'm a wuss. Are you going to be there? Oh, come on. You're going to be there. No? Yes? Nope. I had my phone connected. I apologize, it's not there. And then I don't think the overhead view will work either, or will it? Because it was there. Is it going to show? No, sorry. It's just an overview. But so that was the last of those. I have all my sources on this last page. But I do want to talk about this map a little bit and give you a chance to come up and look at it. So if you didn't already, this is the Mint Canyon Quadrangle. So we are, oh, thank you very much, Glenda. We're way down here in this little corner. But here's the San Gabriel. First off, let's do with what we know. Here's the Sierra Highway. Here's the 14, okay? Here's the San Gabriel Fault. And there's a little dotted line that curves in there, and that's the Placerita Fault. Again, it's dotted because they're not quite sure where it is, but they know it's in that region. And this white area that says QA, which stands for Quaternary Alluvium, which basically means the stuff that is historically present, current, last few thousand years, washing off the hills, right? Alluvium, the stuff that comes down off the mountains. So this whole valley, our whole little canyon, is Quaternary Alluvium, which you'll notice so is the main channel, and so are other channels along the way. But so that, if you know, when you have a chance to come up and look, you can see that. Sorry, it's such a small corner. Oh, and then here we have a cross section of the what's mapped, A through B through Mint Canyon. I lost A through B. Well, anyway, it's got Placerita oil field with the sediments. Here we have Placerita Canyon right there, but it's this whole area. And then we have the San Gabriel Fault. This was the Whitney Canyon Fault to the west. And then the San Gabriel, southwest. And then the San Gabriel Fault, and then on out through Sand Canyon's way up here. So we can see that this is just a really great basin on this side of the San Gabriel Fault with all of these sediments. And the different colors and patterns reflect different things. As I mentioned, QAL is Quaternary alluvium, but we've also got QLS in some places. That means landslide debris. Does not include 94 events, so they're larger landslides. Yes?
Yeah, we know about the alluvial flow here because when we've had huge rains, the creek has flooded quite a bit all the way over the road. And often the guys here have to, you know, bulldoze, shovel, whatever, the parking area, the street, the road. And one big catch basin is the creek is channeled in a tunnel underneath Placerita Canyon, and they have to go in and dig it out.
Oh, thank you, because I always thought, where does it go? So thank you. Okay, cool. Well, something, because this is all Quaternary alluvium is what it says, but then QG, which is unconsolidated alluvial sediments deposited by streams, late Pleistocene, so they've been dissected. So they're the alluvium we see on the hill slopes, right, that have been dissected by water flow since then. So that's really just us, but you know, and then if you want to take a look, this talks, we've got the Saugus Formation, not so much in our valley, but heading out, we've got Saugus Formation, Pico Formation, Towsley Formation, Castaic Formation, Mint Canyon Formation, Chick Canyon Formation, and then the Vasquez Formation. And then marine clastic sedimentary rocks, which are here and there. So if you want to come take a look at this, you're more than welcome. So that's all I have for this part of the presentation. The question is, what is it doing outdoors? To show you, had we not been able to go outside, I think we're going to visualize, to tell you to close your eyes and pretend you're going up to the water tank. And we can't get the aerial view right now, but you saw the map. And if you have, once this will be posted, you'll be able to see it. What it is, it's an aerial view, and then it turns to the geologic map back and forth. So we talked at the Walker cabin, we saw the metamorphosed rocks, some of which are more. Across the bridge where it's straight right there, most of the rocks are pretty rounded, not all, and there are very few fine sediments. Then we worked our way up the hill to some in-place, what I'm calling a metagranite. This is not fully metamorphosed. It's very close to a gneiss, right? Black and white stripes. And we still call it a metagranite, meaning metamorphosed granite. So first shot, they're fairly horizontal, but just a few feet up or down the trail, and I apologize, I don't remember. They're really steeply tilted. Now, that could be that there's a small fault right there. It could be that the piece here sort of fell down and ended up that way, but we do see different angles of the rock within it. Again, looking pretty much from where we were, of course, so here's Placerita Canyon Road. Here's all those sediments, those river deposit sediments over thousands of years. And then you can see the San Gabriel's in the back, and you can't really see, but the Placerita's over here. Here is a close-up of those beds I showed us from down in the parking lot, and you can really see the gradient. But what's interesting is this is going the same direction on the road. Hello, where'd my little mouse go? Hello. I hate when I do that. Anyway, the ones on the right are left, we can see the different sized beds, and they appear to be tilting generally upward, what would be east as you head east. But here we are a little farther, there it is, farther down the road, and they're sloping down to the east. And what that means is that this hill, either one or more have been uplifted. It may be a smaller anticline, right? We may be looking on the western arm or limb, and then the other limb here. But it's also dissected. It's sometimes hard to tell exactly where would be the axis is, right? Because it's curving at a point, the peak of the A. But we can
Tina?
see
Tina, this is on Placerita Canyon. The
east
one
of
on-
us. Oh, go
On
ahead.
Placerita Canyon. The one on the left is on the south side, and the one on the right is a picture on the north side of the road,
Okay,
same
I
road.
thought this is the one I took, but okay.
Oh, these are the ones
All
you
right,
took,
maybe
sorry.
not, maybe not.
Sorry.
In which case, they're both going the same direction, so let's leave that unclear. I know I took some, you took some, but I don't remember, sorry. And then there's our own Placerita Falls, heading through along the creek. This is from up on the hill, not as high up as the water tower, I think we're on our way down. Anyway, so here's the creek, and here's the Placerita Fall generally running through here. Again, the San Gabriel is between this hill and that hill. And then as we go upstream a bit, it begins to meander. So we begin to see some of the curves we talked about that are happening in that floodplain. And then, this is as it leaves the valley. Hello. So this is headed off to the west. And we can see as it goes downhill, and this is at the base looking left, and this is from more on the road looking sort of straight ahead and to the right. So those are all the flags I had. I just thinking we weren't gonna be able to go outside, I wanted to include those. So, thank you all very much for your patience.